Hello, it's James from XRobots.co.uk. This is part 3 of Robot X, the reconfigurable sci-fi robot. I built this project out of 3D prints and Aluminium 2020 extrusion, which makes it easy to reconfigure and change as we go without printing massive parts of it. So all of these brackets are 3D printed, some of them are ABS and some are ColorFab HT, which offers really good layer bonding and it's incredibly tough. So we have the ability for the legs to rotate on these bearings. Have a look at last time for that. Those are locked for now until we put an actuator in, but the rest of this has lead screws in drill motors which are going to drive the joints. And that should make it quite rigid. There is a bit of wobble in this at the moment, and I discussed improving those actuators last time by putting extra nuts in, possibly putting linear rails on. It may be we get rid of those motors altogether and do something else, but we can easily change those out as we go. So I'm going to make a few small refinements this time, and then we're going to look at building up the upper body and mounting some electronics. I've got one minor change to make to this really, which is to move these actuators closer together at the top, because that'll give better angle on the leg there to brace the legs apart so they don't flop together as much. There is still some play in these actuators. I'm still waiting for the extra nuts to arrive, so I can put 2 nuts for that lead screw to screw into, which should make it less wobbly, but those are shipping from China and I don't have them yet. The top ones aren't too bad in all fairness, it's the ankles really that are suffering, and I'm hoping with that extra bracing that'll just make those legs a bit more stable. I can make that change pretty easily just by sliding these bits of aluminium extrusion closer together. Those on right angle brackets on the inside here. Hopefully you can just see that corner one, there's another one there. So we can undo those and just literally slide the aluminium closer to each other, and that will change the angle. I may well turn these around. I don't know if you can see that the actual nut holding it there and the bolt is off centre, so I'll turn them round so they're closer together in the middle, and that means this is less likely to twist, because the angle will be pushing it kind of across in the same direction. We also need to make a piece to fit on top of these to stop them just swivelling, and that will be part of the battery holder, which I believe is going to go in this section in the future. I've moved these closer together, but all that's holding them is these corner brackets I mentioned, and that means they could still rotate. So I've made a plate to fit over that, which I'm going to bolt down to hopefully stop it rotating. It'll also give a bottom to this, so if I put batteries in, they don't fall through. Here it is, it's bolted on with 4 socket caps and the drop-in T-nuts, so that should hold those pieces of aluminium nice and rigid. My actuators now face in, which gives quite a lot more cross-bracing, so this is a lot more rigid. I do have a slight squeak over here somewhere. I need to put some more lithium grease in that joint. But now my legs tend not to sag so much when I put load on the other one. Of course there is a bit this way because the actuators are still loose, but when they're braced together this gives me a much better structure. So it's time to build in some sort of way of reading the feedback on the joints here so we can control the positions, and a few people have asked me about this and suggested perhaps I use linear slide pots like this one. It's a bit like a fader on a mixing desk. This is from a very old project, sort of mounted on here somewhere, and as the linear actuators pull in and out, then that will measure the position. But in fact I'm not actually going to put the feedback on these actuators at all. I'm going to put it on the actual joints. So I'm going to use a pot like this, which is a rotary pot. This is a heavy duty wire wound one, and I'm going to put one of those on the axis that tilts sideways here, and another one on the axis that tilts forward and backwards, and that will probably live inside the leg on a crank like it did on the Gonk droid. So what we'll end up with is 2 PID controllers. We'll end up with one with this pot, and that's going to basically add the value to both of these and subtract it to move the other way, so both of these push and pull the leg backwards in relation to the required position on this pot. And that's all well and good. But obviously then we've got the other one at this angle, so that PID controller is going to have to subtract the number from one actuator and add it to the other one, so that does a push and pull effect. And this is all going to work out rather well, because if we need to move the leg forward and backwards, even if these motors aren't matched, we drive both the motors in one direction, but say one is faster than the other, so it starts to tilt the leg over, then this PID controller, still running and adjusting the motor speed 50 or 100 times a second, is going to come and say, hey, well, I need to basically adjust the motor speeds now because there's an error, so it'll speed up one and slow the other one down to put it right. So this will still move forward and backwards dead straight, and of course we could modify the demand position on either PID controller, and the motors will move accordingly by mixing the outputs of the 2 PID controllers to get the total motion for the leg. And that way I don't need to work out any trigonometry. If I measure the actual linear thing here, and I have to start working out trigonometry to get the actual axis where I want. But if I put the feedback on those axes, I can just drive that demand position and everything else will take care of itself. So I've planned some brackets to hold my pot here. So what I'm actually going to do is stick the shaft of the pot in the where the axle comes through here, because this piece is really wide, and if I planned this I'd have probably planned a cutaway to put the pot. So we've got a captive nut and a bolt that basically holds that shaft at the moment, but it's more than secure enough because it's held at the back and the front, and this piece is extremely rigid. So we're just going to push the shaft back, shove the pot shaft in there instead, and screw it down. And then I've got this bracket here held on the piece that rotates, and that's going to hold the pot body. And I've also designed this bumper on the front so it doesn't kick its pot and damage it at any point. We may need to put some other stuff on the front of the foot, but that'll do for now. Hopefully it doesn't look too weird. And at the top of the leg we've got a similar thing, so we've got a holder for the pot body, and I've just brought this bracket down, and again I've put a captive nut in to hold that pot shaft in line. So we'll get those printed and see how they fit. Here comes one of my bumpers. It's about halfway done, and this is printed in ColorFab HT, and we're about an hour and 20 in. Here comes some of my pot brackets. These shouldn't take too long, but there is one really tall part on them. Right, so I've pushed the shaft back about 20mm, and I've got my pot mounted in its pot holder. So that will just go in there, and that will screw onto the aluminium extrusion there. And obviously as the foot rotates about that axis, then the shaft will be gripped in there and the pot will turn, and I can measure the position. Right, that's both of those installed, along with these stylish bumpers I made, which I think look rather good. Here are the top ones, which are very similar. So we've got the pot constrained in there. Then we've got this thing with the grub screw again, which fits on there, and that measures rotation at about that point. Here it is installed, so it measures the rotation of the top point against the bottom point around that axis there. So we've got 4 pots installed now that measure leaning side to side around those ankle and hip positions, but now we need to measure the leg going back to front, and basically we need to measure each of these. And since they're parallelograms, they're actually all the same angle. So what I've done is put this piece in here, which mirrors that angle, because I don't really want to stick the pot on because it will clash with the motors. There's nowhere really for it to go in line with the actual joint, other than sticking right out of the outside there. So we're going to make this thing that's in line with the same angles, and it measures the same angle around this point. So our pot mounts on there, and we've got this arm with a crank that comes down, and all of these hinge points are exactly in line to make a perfect square. So as this parallelogram moves, this will mirror the same angle. Here's one of them. So now I have another 4 or another 3 to make, so I've got 4 in total. I fitted all 4 of them, so they go across that angle there. So they follow that parallelogram angle. There's one of the ankle ones, so now I have 4 of those altogether and 8 feedback pots in total. But now it's time to think about what goes on top. I decided first of all I'd plan where the various features go, mainly the shoulders on top. So I drew a stick man on top here, and basically its waist point, about where those pots are we just fitted in fact, are exactly in the middle there. So that's exactly half the height of the whole thing, and the thing is coming out at just over 1.5 meters, so pushing 5 feet tall, which was the original plan. So I think that's about the right proportions. Obviously the head and the arms and things will change depending on what character I build on top of it, and the plan is to make that different in lots of little mini series. So I've kept this blue bar at the same point of the shoulders there, in the same position. So for now there'll be no arms, but basically I'm going to use this bar to put some weights on to simulate where the mechanics would be for the arms, and I can load that differently to see what the response is. So the hips are already quite heavy, but in terms of shifting around, we don't want too much weight at the top, but we do want some to sort of simulate the rest of the body mass. So this is also going to move backwards and forwards, so we've got an additional pivot point here. This is very similar to what I did with the Gonk droid to hold it stable front to back, which is an independent axis which will be IMU driven. So that hinges at the front. It mostly hinges forwards more when it takes a step than hinging backwards. So obviously it can move right forwards but not backwards very much, but it can move backwards a bit. And on this part we're going to build the rest of the torso there, or at least a frame to hold the electronics and leave space for those shoulder motors. This is what I have so far. So I've put a couple of brackets on here which will be kind of ribs to give that body a bit of a definition there. Obviously the hips here is basically the lower torso up to sort of probably overlapping where the rib cage would be on a human. It's quite a big thing to get that bracing in. Check out the video last time to see why that's so deep. And I've just put a frame on the top here to hold the shoulders, so that's going to hold this bar to put some dumbbell weights on, and we've got some caps here which are going to stop them falling off, and a couple of brackets. And that's pretty much it for now. We do need an actuator to push that backwards and forwards, which may be up the spine or it may come across. I don't know if that's a linear actuator or another 3D printed motor and gearbox like we have on Ultron for instance, but we'll plan that a bit later. So we're going to have some electronics on the front. I've left some gaps here to put a kind of cage on to protect them, so that will stick out the front to give it some chest definition, and in the back we'll have the motor drivers, and that's pretty much about it. Here's one of my clamps that's going to hold the weights on that shaft. This is one of the main pivot points for that front axis. Got quite a way to go on that yet. I have a number of printers all working away at once, making all the other parts. Here it is, so that's ready to go on. I've got all of the bits and pieces attached, and the place there for the nice bar to go through. And I've put extra bracing on here on all three of the angles to hold this nice and rigid. Right, there's my pivot point, and I've got grub screws holding that piece of 6mm in there, so that pivots rather nicely now. The only issue is, of course, I need to get an actuator in here still to push the legs apart at some point, so I might have to cut that shaft and just have it stuck in these, or redesign the brackets, but for now that's perfectly good. So obviously that will lean backwards and forwards with another actuator as it walks, but for now I'm going to lock it in place with a couple of brackets, so I don't have to design the actuator right now, and we can do that when we get it walking. For now I've just put on two 1 kilogram weights and those clamps to hold them on, but obviously I can reconfigure this so I can simulate different mass distributed throughout the body. So here it is. Obviously the shoulders will be here, so this is just the middle of the shoulder joint. There'll be more stuff there, so I've left a gap for it with the head on top. Kind of comes up to my shoulder height, so it's pretty much the right height, and this is still feeling pretty good. I found in the past the heavier robots were more graceful because they don't move as quick. Obviously it's quite a lot heavier than the Gonk droid, so it must be up to 25 or 26 kilograms now, especially with these weights on. But on the whole, feeling pretty happy with that. We may refine the actuators as we go, but I'm pretty sure that that's going to work okay. So let's think about some electronics mounts. So at the front we're just going to have a blue panel here with a slot in, and I'll solvent weld mounts for the various electronics, so those are in the front, and I've just made some sides here which will be in Colorfab HT, so they're nice and tough. I've left screw holes to put a front cage on. I'm not sure if I will or whether I'll just leave them like that, so basically if it bumps into something or falls over it doesn't smash the electronics. In the back I'm still deciding what to do. This is for all the motor drivers. I think they're going to fit there somewhere on a bracket so I can get to them, and there's still a slope there clear for the back actuator, however that works. Here comes my main big blue panel with the slot in. And that of course is one of the side panels. Here's that motor driver mount. We've still got some things to make to actually mount this plate, but it's looking pretty good. Those bits and pieces are installed, so all my electronics are going to mount on there, and I'll solvent weld on some posts to screw all the boards to, and as I say, I might build a cage over the front, we'll have to see. And this is my motor driver board, which is going to go in the back there, and we'll have a closer look at that now, and the other electronics. You may remember from my Gonk droid build, I used lots of Arduinos to control it. I had an Arduino Mega as the main brain there, dealing with stability, and then I had these 4 Pro Minis linked to it, each one controlling 2 motors, running the PID controllers and outputting the PWM to the 8 motor drivers. So I'm not going to do that for the new build. I'm going to use this board, which looks very similar, but it's actually an Arduino Due, and that runs at 84 megahertz and it's 32-bit. The Mega is only 16 megahertz and 8-bit, so this should be more than fast enough and more than capable enough of running all of those PID controllers, which is good because it keeps all the variables within one program instead of having some of them back over a serial bus, which means it's hard to get motor positions back to run a state machine on the main Arduino. So instead of having those Arduino Pro Minis dealing with all the PWM outs and dealing with all the PID controllers, we're going to run that on one board, and then we're going to use this board to hold all the PWM positions. And these are basically normally sold as a servo controller, but they will do normal PWM as well, which is slightly different to servo PWM. In fact, it's much simpler to do the code to set it up, and they're quite supported. These are a clone of an Adafruit board, so there's good library support, and it's an I2C device, so I can link a couple of wires to this from the Arduino and control all of my 16 PWMs to go to my motor driver. So here's that motor driver board again. This is the BTS7960 IBT2 board, which you can get for about £7 each in money if you get them from China. There are various people who sell them in the UK and the US on eBay. And these are 43 amp 28 volt motor drivers. I use these in a lot of projects because they're quite cheap. And takes two PWMs to drive a motor in each direction. And this is the battery in and motor out connector. So you'll notice I've positioned these connectors so they're on the edge of the board, so the fat cables can come off the edge of the board. And also I've got a toggle switch on every one there, which is for the motor enable pin, so that I can isolate individual motors and not have them all running when I'm setting it up and I'm testing or fault finding. I'm also going to have this big emergency stop button in series with all those motor enables, so if anything goes wrong I can just cut all the motors off in one go, as well as having a remote switch like I did last time. I've made a bracket here which attaches that motor driver board to some of the 2020 extrusion that makes this up inside. Here it is, it seems to be mounted pretty well in there, so that should be good, and I've already wired all the toggle switches to the enable pins on the back of these boards, so those are all wired in. I need to take one wire out and run that to my big emergency stop switch, which resets like that, and then take that out to the Arduino, so I've got my soft motor enable on the remote, but if anything goes wrong I can do this, or I can isolate motors individually. Round the front I've got my two boards attached. I've solvent welded on some little standoffs for that one, and that one is just taped on. And of course I just need to run the wires for I2C to this, the PWM outs through this slot to the motor drivers. This is a 3.3 volt board, but it will actually run from 5 volts. It's got its own onboard regulator, so somewhere I either need a 5 volt battery pack like I had in the Gonk Droid, maybe a USB boost adapter, or I'll fit another 5 volt regulator to power that, and all of the motor drivers, this and lots of the other things run on 5 volts, so we can basically power everything off 5 volts and let the Arduino regulate itself down to 3.3. We will need some level matching, because this is a 3.3 volt I/O device and this is 5 volts. We need a level matcher for the I2C and also for some of the serial devices like the remote. But that's pretty much it. It seems to have come together quite nicely. Obviously we do have some other things to refine, but on the whole I'm pretty happy with its kind of stability there. Short of actually controlling it, it seems okay. It seems rigid enough. I'm hoping those actuators are strong enough, but of course due to its modular nature we can always change those around. And we do have pairs of motors working together on every joint, either pushing and pulling or both pushing and pulling. So I think that should be strong enough. But I just wanted to add some commentary about sort of bigger, heavier robots. This is on the heavier side. The Gonk Droid was probably half or less of the total weight. So at the beginning of the Gonk Droid series I showed you some older robots that I built in the past, and we're just going to have a quick recap on that on Android 6 and Android 7. And Android 6, the date of the upload of the video here you can see is 2007, but I think that's when I first had a YouTube account because I built this in about 2004 or 5. So let's have a look at that. So let me just explain. This is about 5 feet tall. It's made of wood. This is a room in a house share I used to live in. This is the corner of the bed here. This is a bed sheet hung up, and that's a table, and that's the door. So to just get an idea of the size of the thing. So let's just see that walking along. So it's got parallelogram legs again, and it's got 5 windscreen wiper motors in it. And there's actually 2 in the bottoms of the legs, 2 in the tops, and 1 that makes it lean side to side, and that's in the hips. Now the ankles here don't have any motors, they've just got end stops, and that's about it. So you can see from the size of that thing, it's all made of plywood, and all of the metal is studding basically with lock nuts on, so that thing weighed quite a lot. And you can see it quite gracefully move side to side, even though the top swings about, because it doesn't have any independent ankle and hip motion, so it's literally shifting its mass by moving its body. So you can see that moves at a fairly slow rate and walks along fairly convincingly. This is Android 7, which was the next one, and this walks a bit more like a human. This is what I want to get out of Robot X. So again, it's a similar size. And you can see in fact that the body swings the opposite way, so the hips swing to shift mass. This robot only had 3 motors in it, so you can probably see if we just go back a bit, these motors turning in its hips here, and those are pulling strings, pulling the parallelogram legs, and there's only 1 motor per leg. There's a lot of bungee cord in it and cords going down the legs, and again there's one in the middle that pulls strings across, shifting those hips. I think this probably weighed more than Robot X just because it was made of, again, lots of 2x1 wood, plywood. It's also got cold rolled wrought iron in it, which was strips of basic iron I bought for making gate posts and things. So a lot of this was sort of stable by bungees. It had no stability. In fact, neither of them had an inertial measurement unit or any proper processing in them. The control system for both of those is this lovely looking thing, which is actually quite chaotic. So what we've got in here is a number of PIC chips, and all of those are sitting on a serial bus so that they can receive serial data, and all they do is turn a number sent to them over a software serial as well at 2400 baud, so it's pretty slow. And it takes that serial value and turns it into 8 parallel bits, and that's what all these wires are. And all of those go to digital to analog converters, and somewhere on here, yep, there's a bunch of op-amp followers. So basically the result is I can send serial data to these on a common serial bus, and this whole thing produces 8 analog voltages that come out of these pins here. And the next stage of that is those analog voltages get sent over to these boards, and each one of these modules basically controls 2 motors. So they're actually relay H bridges that can switch a motor in either direction. And you'll notice some more things on here. These are op-amps and some little trim pots. And what that does is compare the voltage sent from this with a slide pot that I showed you earlier in this video, in fact, which was attached to the joints. And basically it gets the error and switches one relay or the other relay, and the dead spot is tunable with this pot. So in the middle the motor's off, and basically it will match the position of the motor with the voltage here that I've sent to it. And this whole thing was controlled by, I think, a QBasic program or something similar on a PC, sending data over a serial port on fixed timers, just saying to move the motors to fixed positions on fixed timers. Obviously there's no speed control or acceleration or deceleration control. It's on or off. And obviously in Android 6 there, we had 4 of these because we had 5 motors, and this system would control up to 8 motors. So obviously we had quite a lot of relays clicking around as the thing was walking along. And that's how they worked. There are some pictures of those Androids on my website. Unfortunately, YouTube didn't really exist then, so there's no video series, but have a look in the older Android section to see those being constructed in pictures. And the motors I was using were these, which are windscreen wiper motors, which you can see are quite a bit bigger than the motors I've got now. However, I was actually running, these are 12 volt motors, I was running them on 5 volts on a PC power supply, so they didn't go too quick. And all that's in here is one worm gear reduction. So that's not really as efficient as what I've got here, which is these motors obviously with a planetary gearbox and then the lead screw, so the motor can run at full speed to get full torque instead of having to run them slower to make them go slower. And we can change the pitch of these lead screws if they're too high so that we can get them to go, say, half the speed with twice the force. And of course we've got 2 motors working together to do everything. So I'm hoping these motors are going to be up to it. As I said before, we probably do need to refine these actuators because we've got quite a lot of wobble in them. We've got to change these piston parts and put extra nuts in. And if I have to redesign the whole thing, say perhaps there's a fixed lead screw on a slider with a proper track and a flexible coupling to this point, then we can do that because we can just bolt it onto the aluminium frame. So I'm pretty confident with the mass of this and the motors I've got, that should be okay to make it operate. That's all for this time. Next time I'm going to be wiring up those electronics and trying to get some basic control over the functions. We've still got to fit some inertial measurement units, which I'll be talking about next time, and whether it's going to be stable or not straight away I don't know, but we should be able to get control over all of those joints and show how those perpendicular pots control the PID controllers to get the 2 motions moving forward and backwards and left and right in each joint. So don't forget to subscribe for more updates on this project and other projects, and also check out my Patreon campaign at patreon.com/XRobots, where you can get access to some exclusive rewards, including all my videos early and a live broadcast with me. Also check out my t-shirt store, the links are in the description to this video. I have a limited edition design which ends at the end of January 2017, and after that hopefully there'll be another one, so if you're watching this in the future you can still check it out. Alright, that's all for now.